Hello and welcome. I hope you are having a great day. In this video, we are going to understand what is soft margin SVM or support vector machines. So let's begin. So what's the intuition? So earlier we have understood hard margin SVM. Okay, so it's like a we are dividing two sides. So for example, if we have a division, say we have this black line as our design boundary and we have this purple lines as our margins. Okay, and we have red points on this side and blue points on this side. So hard margin SVM says that none of these points, okay, can be within this is the descent boundary, this is the margin. None of these points can come within this range, okay, in this range. It's very hard. All these points should be clearly demarcated and classified in two different buckets. It cannot come. If it is not able to find this, then it will not work. It's like a steel fence. It is not, nobody can cross the boundary. You cannot have a red point here or here, okay, so it cannot cross this side. So that's the requirement of hard margin. But in real world, we may not have that case. So there can be some points which may not be like exactly, there are some noise, some outliers, sometimes some point cannot be clearly classified. So there should be some flexibility to let the algorithm work even if it is not clearly demarcated. The data point are not clearly separable or linearly separable. Even then it should work, because real world data is has lot of missing data. Okay, it's not clean. Okay, it's not clean. It has a lot of noise. There are a lot of human error. Something is labeled, a cat can be labeled as dog, a human error. So mathematically it's a cat, but it will be labeled dog, so it will not be able to classify that well. I hope you get the point now. So real world problem is, real world data is messy and we need to deal with that. And for that we cannot be very hard about the classification, and for that we need soft margin. Okay, so this is made of a kind of porous boundary. Okay, let me show you. And so some points can cross the margin, so it can cross this margin and come on the other side, or it can even get into the margin here. Okay, it can also get into the margin here. Okay, so if it's okay, it's soft margin, it's okay. So it's kind of porous. But if some point crosses, it should be, all of the points should be clearly classified. But if some point comes within the margin, there'll be some penalty for that. So there'll be, you will pay penalty, so that the algorithm learns that these points are wrongly classified. But there is some scope for letting it happen. Okay, so let's see an analogy. So for example, this is your red land people and blue land people. So there's a solid steel fence here, nobody can cross, and these are the margins, so nobody can cross here. So these are like two nations, and there's a iron wall, nobody can cross. Okay, but in, like, we have many countries will not have, so there are some places where we have this, but in some practical cases many countries don't have this steel or steel fence. So there is a porous boundary. You see here, this is a dotted line, there is a porous boundary. People can cross from here to there, no problem. So blue people can come here, 100 people can go there, some of them can be here, and that's okay. Okay, that happens in real world. Okay, that's the idea. So it allows, this soft margin allows crossing of points to the other side. I hope this analogy makes it clear. How it happens mathematically, let's see that now. So here we have the descent boundary, the main descent boundary. This is your W transpose X plus W naught, and these are your margins. Upper margin, that is +1, and the lower margin is -1. W transpose X, okay, plus W naught is -1. Okay, and this is the width, total width of this. This is equal to 2 by weight. We have seen this in the hard margin SVM video. Okay, and we want to maximize this width so that the points are clearly classified. But here if you see, we have 3 points which are incorrectly classified. Here if you see, this x1, x2, x3, red point has come inside the margin here, x1. So this is definitely, it is inside the margin, not allowed. But this x2 has to cross the descent boundary, it is wrongly classified. Okay, and x3 has like crossed the limit, it has come in the blue side itself. This X3 has crossed the limit, it has come in, so it is totally wrongly classified. It should have not come. So not classified. Basically, this data point is present here. So you have 3 points which have come in, which are wrong, which should have not. These are like noise, or these are the noise points or outliers, which should have not happened, which is making this data not perfectly linearly separable. So we introduce a error term here. Okay, we introduce a error term. So distance from descent boundary for positive labeled is greater than or equal to 1, and there are 3 noise points for which it is less than 1. So for positive labeled points, if you see, this distance is greater than equal to 1, right? So all these on the boundary will have 1 because this is the 1, and for all these points the distance will be greater than 1. But for all these points this is less than 1 because this side is plus 1 and this side is also distance wise. If you see the magnitude, this is 1 only. Okay, so but for this red point the distance is less than 1. This is 0.5 only. Okay, and when we also include the sign, we'll see the calculation how do we include this in our error term. So this is less than 1 definitely for all these 3 points, because it should have been 1 here and it is less than 1 for all these 3 red points. Let's see how do we include this in maths. So we introduce a slack variable or error term. It is pronounced as xi, this E kind of symbol. This is called xi. This is a Greek alphabet for every single data point. So for the point which is correctly classified, that will be greater than 0, and that will be equal to 0. This error term will be equal to 0 for correct classification. We'll see that. So what is yi into w transpose x should be greater than or equal to 1. That was our constraint earlier with hard margin SVM. We also introduce a error term xi here, xi I for each data point, and that will subtract from 1. So earlier in hard margin SVM we had only this term. Now we'll also say that there is some error, and if that is the error, this will reduce it from -1, and now it will not be 1. And how do we calculate this error term now? So error term will be equal to 1 minus the yi into the distance of that point from the origin, or whatever is the equation that is given, w transpose x plus w naught, that is the distance from the origin itself. And also the error term is always greater than or equal to 0. For the correctly classified points, it will be 0. All these points here, these points, red on clearly on the other side of the margin, and all these blue points on the clearly. For all this there is no error because it is correctly classified. So this will be 0. Error will only happen when the red one crosses this side. It comes within the margin or it goes to other side. So we'll understand this with the help of red points. Okay, let's see. And so my xi will be given by max of either the maximum error can be 0, or if the error is more. Okay, for the correctly classified points it will be 1, and since this is 1 minus, so yi into w transpose x plus w naught. So this is plus 1. Say for example for plus 1 this is plus 1, and yi label is plus 1. But for the points which are way beyond this plus 1, so this side will be greater than 1, right? For here w transpose x plus w naught is greater than 1. Okay, so where the w transpose x plus w naught is greater than 1. So for this the error term will be negative. Okay, so for these points here, for all these points the error term will be negative because it is 1 minus the label into this. So this is 1 minus some greater than 1 term. So for these this error term will be negative. So for this, for all these negative, I am not telling, for all these negative I make it at 0. That's the max value, means you are correctly classified. If your error term is going to negative zone, means 0 or less than 0 means you are correctly classified. You are on the correct side with correct label. I hope you get the error term logic. Okay, so this is negative or 0 is okay. So I'll give a max value, means you are correctly classified, and I'll give you the error term value as, for all this the error will be equal to 0 for all the correctly classified. Here also it will be 0 because they are correctly classified. Okay, so let's see. 0 or whatever, if it is maximum, it is whatever is the value. Error term for others which are not classified properly, for them this error will be greater than 0, and we'll see how. So the above error term is also called hinge loss. So this formula for this is also called hinge loss. This is the formula for epsilon. This is also called, this one especially the second part, this is nothing but hinge loss. This has got a name. Okay, what is hinge loss? So it is nothing but, so the error at this W transpose X plus 1, right? So after this error will become 0. For the correctly classified points, the error will become 0. And after and before this, the error will be linear. And if you see, this is like kind of a, if you see, this is a wall, and this you can see this is like a door. Okay, so it's like this. Have you seen this holding the door? These kind of things. So the edge. So you have the edge like this of the door, and it is like holding the door to on the wall. This is called your hinge, and from this the name comes, because this graph shape is like a hinge. So you have a wall, and this is the door, and it can, like, on the hinge it can move. So this hinge is here on the bend. Okay, on the bend you have the hinge. Okay, okay, then let's continue. So hinge loss is cleared. So that is the hinge loss for our error terms, xi or slack variable. So slack or error term meaning this is your xi max of 0, and this is your formula for hinge loss. Okay, so for correctly classified points, error will be 0, as I mentioned you, and for the data points which are within the margin, this will be less than or equal to 1 within the margin, but on the correct side. Okay, so on the correct side means, say for example, where is it? Yeah, here. If you see these points here, so this one, okay, this red point here, okay. So here the distance, it should have been, this is your 1, this is 1 unit, and this is 0 line, this is your W transpose X plus W naught is 0. So this distance for this red point is definitely less than 1, and that's what it is saying. That's what it means. So within the margin means descent boundary and plus the margin. So there's one decision boundary and there's margin on both the sides. So if it is correctly classified means, say for example, these are the red points and these are your blue points here. So if a blue point is here or a red point is here, oh sorry, let me redraw. So this is your descent boundary, this is your margin, and this is your red zone, this is your blue zone. Okay, and say a blue point comes here or a red point is here. Okay, so for them this distance on both the sides is 1. This is 1, this is 1. So this distance of this point will definitely be less than 1 because the margins are at 1 distance. This is also 1. That's what it means, that for these points the error will be, the slack variable will be less than equal to 1, between 0 and 1. And for which, if it's on the wrong side, like if it crosses totally on the descent boundary, it goes on this side, then definitely it will be greater than 1 because it should be here. This is 1 and plus this extra distance. That's what we are saying, that you should have been out on the other side of this margin itself, but you have crossed this 1 unit plus you have gone beyond this. So your error is more than 1 now. I hope you are getting it mathematically. So this is 1 and now this is the decision boundary and you have crossed this, red point has crossed this. If it has come here, you have crossed this line and now your error is definitely more than 1. And you are on the wrong side of the decision boundary, you are misclassified. Okay, let's see for all these 3 points. So epsilon, the noise point that we have, x1, x2, x3 that we saw. For this, the distance is plus 5. So your xi will be max of 0, 1 minus 0.5, that will be 0.5. And the next point which is beyond, okay, for that the distance is minus 0.5. So for that it will be 1 minus minus 0.5, that is minus and minus will become plus. So it will be 1.5. Means it is greater than, it is definitely misclassified. This is within the margin, this one. And this has crossed the descent boundary. And this is further, it has crossed. If it is greater than 2, it has further crossed the width also. It has gone to the other side. Let me show you. So this is the distance for this point. For this it is 0.5. For this it is 1.5. And for this is 2.5. Because this is 2. Okay, this is 2. And this side is 1. And this side is 1. Because this is W transpose X. This is minus 1 and this is plus 1 line. I hope this is clear. So this is how your xi is calculated. I hope xi error calculation is clear. Okay. So that is the main takeaway from this. You have to understand. So what is the goal? To maximize the width of the margin. So margin's width was given by this 2 by W. Okay, we have seen this in hard margin SVM. So this is, and we have inverted this to a minimization. This was maximizing the width is equal to minimizing the weights that gives the hyperplane, and also minimize the violation or sum of slack errors. So all these errors should be minimized. Sum of all the errors should be minimized. That's the idea, right? So I should not make errors after I have created the margin. So my margin should be maximized, and my error term should be, the errors for all those, the margin should be such that that error is minimized. So if this error minimization is not there, the hard margin will keep on, okay, making as big as possible. But because this is soft margin, error term will also come into play, that I have to minimize the error also. So both of this we have to combine together, and this is, I'll show you, okay, in the next. So this is nothing but your regularization term, L2 regularization term, and this is your error penalty or the loss function, loss xi formula will just put, and this will be like a hinge loss. This is error. How do we get this? We get by the hinge loss formula, right? Max of 0 comma and then the error, whatever is the error. Okay, and this is subject to constraints that my point should be correctly classified. This comes from the hard margin, that this label plus the distance from the origin, that multiplication should be greater than 1, and then I give some scope of error that you can wiggle on the margin on some side, minus the error. There is a softened margin constraint, that the margin is soft, not is not hard. Earlier it was hard margin, it should be 1 only, anything cannot come there. So I have some scope of wiggle, and this error should be, this slack or error cannot be negative. The error is always positive, because that is max of 0 comma the other error calculation this we did, right? So this will go this side, this will become -1. From this error calculation can come. And we use a hyperparameter C, like lambda, okay, to control the trade-off. So this is your loss function, and this is your regularization. Okay, the C term, this is your loss function, and this second one is like your L2 regularization, where the weights will be reduced to 0. Okay, so what is the role of hyperparameter C? So if I have a large C, if the C is very high, what will happen? If the C is very large here, it will try to make the errors low, very low. So it will try to classify all the points correctly. So it will make the error 0, means it is trying to fit all the data points, so that error for all the points is very low or close to 0, means it is kind of overfitting. So that's what it says, that if C is very large, misclassifications are expensive, and model tries to keep the error as low as possible. I'm trying to make the error 0 for all the data points, means I'm fitting to all the noise, everything. So that's your overfitting. And in the converse way, if I have small c, means underfitting. So I will try to increase the margin width. That is more important than individual errors. So even if I make errors on the individual terms, means I'm not getting the pattern right, but I will try to minimize the, okay, the margin width should be maximized. So my width of the margin should be maximized, even if the, okay, say for example, if this is my this and my margins are this, so I'll try to keep on spreading this margin, even if my points are wrongly classified, no problem. Even if this is here, no problem, I'll keep on expanding this, because my C is low. I don't care about the errors now. So that's what we have to tune and find out, that where is the where is the balance. Okay, let's see. So let's see the hinge loss view. What is your xi given by hinge loss? That is your max of 0 comma 1 minus, this is your xi. This is the calculation yi into the label, whatever is the value coming from this. So the same equation optimization can be written as, this is your L2 regularization term plus C times your hinge loss. This is your hinge loss of yi comma f of xy. This is your given as a hinge loss, and this is your error term. This is nothing but your xi, right? So this is nothing but, no, this is your loss function plus regularization. So it is like the normal equations that you have seen in machine learning till now. And now this is all difference, but now we can solve it. But solving it is like, now you can use gradient descent, but we cannot use that. What is the problem? Solving this primal problem is difficult using gradient descent. We use other ways to solve this. So this is just, so if let's continue this. So hinge loss view, SVM is nothing but L2 regularized hinge loss minimization. As in logistic regression, we reduce the or minimize the log loss. There we minimize the log loss, right? Binary cross entropy loss. Similarly, here we try to minimize the log loss plus the L2 regularization is inbuilt here. I hope this hinge loss view is clear. And soft margin, the hinge loss view is coming from the xi, and we have spent time to understand xi also. How is the error term calculated? Okay, let's put the both of these into perspective. So we have logistic loss, which is our log loss, and hinge loss together. This is the graph. Okay, so this is your hinge loss is coming from here. So this is your hinge loss, is a straight line, and then it is going after this point, after at 1, this is going at 0, this is continuously at 0, but this log loss will gradually come down to 0. So this is just the loss function comparison for SVM and logistic regression, because both are used for classification. So that's why we compare these two, and we always talk of logistic regression and SVM in same context. Okay then, so we have understood this primal formulation for the optimization. In the next video, we'll understand the primal dual equivalence. So solving this primal equation that we got for soft margin is very hard. So we try to solve it. We do a modification. We try to solve the equivalent dual problem. So there will be some maths that I'll explain, and there will be some maths which I'll not cover, like KKT conditions, etc. I'll just mention them, but I'll not explain it. But we'll do the complete derivation from primal formulation using Lagrangian method. We'll go to the dual. Okay. So next video will be math saving. Okay then. That's all for this video. Thanks for watching this video. Have a great day ahead, and bye for now.